Hi everyone. In this presentation, I will walk through ViSS R1, short for Self-Supervised Reinforcement Video Reasoning. The paper asks a deceptively simple question. When a multimodal large language model writes a long chain of thought for a video task, is it actually using the video, or is it mostly reasoning from a few sparse visual hints? The authors argue that many current R1-style video reasoning methods are still too text-centric. They may learn to produce convincing reasoning traces, but the dense visual and temporal information in the video remains underused. ViSS R1 tackles this by bringing self-supervised visual transformation tasks into reinforcement learning. The goal is to make the model inspect the visual input first, understand what has been changed, and only then answer the real user question. The motivation starts from the standard R1 pipeline. A model is first supervised, fine-tuned on chain-of-thought style data, and then refined with reinforcement learning algorithms such as GRPO. This works well for many language problems, and it has also inspired recent video reasoning systems. But videos are not just long captions. They contain motion, temporal order, scene transitions, object interactions, and causal clues. Existing video R1 methods often treat the video as contextual evidence and extract only a few sparse cues to support text reasoning. This creates shortcut learning. The model may answer from one frame, or from the options in a multiple-choice question, instead of really modeling the full video. The paper also includes a frame masking analysis. When many frames are masked, previous video R1-style models do not always drop much in performance. That is a warning sign. If removing visual information barely hurts, the model was probably not relying on it enough in the first place. The key idea is to use self-supervised pretext tasks as rewardable visual reasoning problems. In classic self-supervised learning, we can transform an input and ask the model to recover what happened. For images, the paper uses rotation, flip, and puzzle-like patch swapping. For videos, it uses three-dimensional rotation, reverse playback, and clip shuffling. The important part is that these tasks do not need manual annotation. If the training pipeline rotates an image by 90 degrees, reverses a video, or swaps two clips, the correct answer is automatically known. That makes the task a natural fit for reinforcement learning with verifiable rewards. Instead of rewarding only the final answer to a user question, the model can also be rewarded for correctly identifying the visual transformation. This forces it to pay attention to spatial layout and temporal order before doing language-based reasoning. The first method is called pretext GRPO. Think of it as a visual warm start before the normal user question reinforcement learning stage. During pretext GRPO, the model does not train on the original user query. Instead, it receives a transformed image or video and a multiple-choice pretext question, such as, "Has this video been reversed?" or "Which two video clips were shuffled?" The reward is simple: 1 for a correct transformation answer and 0 for an incorrect one. The optimization objective is otherwise the same GRPO-style objective. After this visual warm start stage, the model goes through standard GRPO on real user questions. The paper calls that full sequence pretext GRPO plus. The attraction of this method is that it is easy to insert into existing R1 pipelines. Its practical downside is that it adds another training stage with a different objective, so the training process becomes slightly more complex to control. The second method is the full ViSS R1 framework, and this is the cleaner integration proposed by the paper. Instead of separating pretext learning from normal R1 training, ViSS R1 uses transformed inputs throughout both supervised fine-tuning and reinforcement learning. The model receives a transformed visual input, a pretext question about the transformation, and the real user query at the same time. To make this output controllable, the authors add a new transform tag to the response format. The model writes its reasoning inside think tags, the transformation prediction inside transform tags, and the user answer inside answer tags. During reinforcement learning, the reward has three parts: a transformation reward, an accuracy reward for the real question, and a format reward. This design changes the behavior we want from the model. It should not jump directly to the answer. It should first identify how the video was transformed, implicitly reconstruct the original visual sequence, and then solve the actual task. Before looking at the results, it is useful to understand the experimental setup. The base model is Qwen 2.5 VL 7 billion. The training data comes from the video R1 pipeline, including the chain of thought data and the reinforcement learning data. For ViSS R1, The authors reprompt Qwen 2.5 VL 72 billion to construct transformation-aware chain of thought supervision, so the smaller model learns the new output format before reinforcement learning. Training uses mixed images and videos, with 6 transformation families in total. The evaluation covers 3 video reasoning benchmarks, VSI Bench, Video MMMU, and MMVU, plus 3 broader video understanding benchmarks, MV Bench, Temp Compass, and Video MME without subtitles. This makes the evaluation reasonably broad. It includes spatial reasoning, professional video understanding, temporal comprehension, and general video question answering. For experiments, the authors use Qwen 2.5 VL 7 billion as the base model, with training data derived from Video R1. The evaluation covers 3 video reasoning benchmarks, including VSI Bench, Video MMMU, and MMVU, plus 3 video understanding benchmarks, MV Bench, Temp Compass, and Video MME without subtitles. The results are strong. Pretext Group Plus reaches 39.2 on VSI Bench and 53.9 on Video MMMU, outperforming Video R1 by 3.4 and 1.6 points respectively. The integrated ViSS R1 model achieves the best reported score on Temp Compass and Video MME among the compared open-source R1 style models in the table. Relative to the Qwen 2.5 VL baseline, ViSS R1 also improves consistently on reasoning-heavy benchmarks. The key interpretation is not just that the numbers go up. The improvement suggests that self-supervised visual rewards can complement outcome-driven RL and make video reasoning less dependent on shortcuts. The paper also studies hallucination and robustness, which are especially important for multimodal models. On Hallucination Bench, some ordinary R1 video models actually perform worse than the base model, indicating that optimizing only for final answer rewards can amplify visual hallucination. ViSS R1 is much more stable. Its answer accuracy is close to the base model, while its figure level and question level scores improve. The transformered video evaluation tells a similar story. When videos are rotated, reversed, or shuffled, Video R1 and Video RFT suffer larger performance drops. Pretext Group Plus and ViSS R1 lose less accuracy, especially on Video MME. This is exactly what we would expect if the model has learned to reason about transformations during training. It is not merely memorizing answer patterns. It has been trained to inspect visual structure and temporal structure as part of the reasoning process. The ablation studies clarify what matters. First, image-only pretext tasks are already useful, because spatial understanding transfers to many video tasks, but video-only pretext tasks perform better overall, which confirms that temporal representation learning is essential for video reasoning. Second, the training paradigm matters. SFT-only training teaches the model to follow the response format, but it does not fully unlock reasoning ability. RL-only training can be strong on some benchmarks, but it becomes unstable on tasks that require well-formed outputs, such as regression-style questions in VSI Bench. The standard sequence, supervised fine-tuning followed by reinforcement learning, gives the most robust behavior. Third, reward weighting matters. The transformation task should help the real task, not dominate it. The paper finds that setting the transformation reward to 0.5, while the real answer reward is 1, gives the best average score. If the transformation reward becomes too large, the model pays too much attention to the pretext task and loses focus on the user question. To summarize, ViSS R1 is not about making the model write a longer chain of thought. It is about turning visual inspection into a trainable and rewardable step. By using self-supervised transformations such as rotation, flipping, puzzle swapping, reverse playback, and clip shuffling, the model is pushed to examine the visual content and temporal order before answering. That gives us a useful lesson for multimodal reinforcement learning. Do not only reward whether the final answer is correct, also design auxiliary tasks that force the model to use the information we care about. For future video agents, this may be more important than simply asking for longer textual reasoning. A model that reasons well about video should not just sound thoughtful. It should be trained to look, restore, and then reason.